Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members that's official.
Just to reiterate again for everyone that's in the class. Again, we have all our friends from industry, the various database companies on campus here today and tomorrow. And then tomorrow morning, they're having all the info sessions. I posted this on Piazza. It's on Piazza. Or it's on the website too, right? So again, if you're in the class, by all means come to this. And if you haven't yet put your CV and your availability on the spreadsheet on Piazza, please go ahead and do that. I think there's actually going to be a bonus info session at 12:30. I think the Confluent guys are actually decided to come in the last minute. So I'll post on that Piazza where that would be. I don't know what room it is. So again, start at 9:30. And again, I basically took everyone's preferences, asked ChatGPT to write me a linear program to come up with the optimal schedule. And this is what it produced based on availability and preferences. So it looks reasonably correct. OK? Any questions about this? Again, these are like informal sessions about like they'll describe here's what their system is doing. Here's some of the problems they're working on. Here's what internships and full-time positions look like. OK? And we like all these people. In some of them cases, like Weaviate sent their CTO, the co-founders here from Germany. And then the ClickHouse guy, I think he's coming in from the Netherlands as well. So these people, you can ask them technical questions and they'll know the answers. OK? All right, awesome. All right, so last class, we were focusing on the first problem here, right? How we're going to represent data for their database on disk. And so today's class, now we said, OK, now that we know what things are going to look like on disk, we need to bring it into memory to do something with it. So that's what this discussion is going forward. And this lecture would be, OK, how are we actually going to facilitate that movement back and forth? And how do we keep track of what do we have in memory and what needs to get written to disk at certain times, right? Again, the reason we have to do this is because of the von Neumann architecture. We can't operate directly on disk data, data when it resides on disk. There are specialized disks that can do that. Like Samsung will sell you an SSD that you get ARM cores on it, and you can actually program, do stuff down there. But for general purpose systems, we have to assume we got to bring it into memory, right? So today's really about, OK, how do we do this, and how do we make it look like we have more memory than we actually do without slowing things down? So there's two main things we're going to try to optimize for. The first is the spatial control, which is where things are actually going to be physically located on disk. And the idea here is pretty obvious, that we want things that are going to be used together to be stored together on disk. Maybe not necessarily in the same page, but contiguous pages, right? So that way we at least try to do some sequential access to go do one I/O or one fetch and go bring a bunch of stuff in, right? Some systems, like in Spanner, for example, you can actually do denormalization, meaning like I have two tables, and this tuple has a foreign key relationship to the other tuple, and I'll pack in the tuple from one table inside the other tuple, so that when I do a join, the data is all on one page. But again, most systems don't do that. The other approach is, the other thing we're going to optimize for is temporal control. So this would be when we have to read things into memory, we want to try to keep that thing in memory for as long as possible for as many queries or operations that need it, and only evict it when we don't think it's going to be used. Right? Worst case scenario is that we read a page, do something with it over a query, throw it away, evict it, free the memory, and then next query comes along and we just read the same page again or go back to disk yet again. We're basically thrashing things back and forth, right? Because we want to avoid the long stalls from having to read things from disk, because disk can be significantly slower than memory. And so we're going to see in our buffer pool replacement policy and in our write-back mechanisms for the background writer that we'll try to choose things that to evict if we think it's going to be unlikely to be used, which is not always easy to do. So this is a high-level overview, again, of the diagram that I showed in the beginning. Oh, my monitor fell off. Well, if the cops call, it's here. All right, as long as it's on, that's all they care about. All right. Yeah, that one's OK. OK, so here's our disk. Our database is a bunch of files on disk, and this can be broken up into a bunch of pages, right? And whether it's an LSM architecture or the heap file, for our purposes here today, we don't care. And then now up above in memory, we have this thing called the buffer pool, and it's going to be comprised of a bunch of frames. And think frame is going to be the same size as a database page, right? We just call it frames because it's can't use the term slot, but it's the location where we can put a page in our memory. And the buffer pool manager is responsible for managing the contents of memory. And then up above, in higher abstraction level in the system, we have this execution engine thing, which we haven't talked about yet, which will come later on. And the execution engine is going to run a query and say, hey, I want to get page 2. And it got page number 2 from the record ID. Remember I said that the physical identifier for a tuple would be some record ID, would be comprised of a file number and maybe an object number, and a page number and a slot number. So given us the page number, we can go to the buffer pool and say, hey, we want to get page 2. Well, the first thing it's got to do, if it hasn't done it already, is bring in the page directory, because that's going to tell us where to find the page 2. Then we go jump to that offset in our file, copy in page 2, and we're going to put it in some free frame in our buffer pool. And again, this basically would be a mem copy. We're going to copy the contents of where the page is on disk and put it into memory. And then now what we're going to get back to the execution engine is a pointer to page 2. And then page 2 can do whatever it wants to interpret the contents of that page, right? The bytes in it, by reading the header, looking at the catalog. If it's an LSM, it knows how to parse whatever's inside of it. You okay? What do you got?
There's a lantern point.
Just step on it.
Yeah, there we go.
All right, done. All right. Is that better? Okay. All right, so, and then so you can do whatever it wants with page 2. All right, so then now say the execution engine finishes whatever that query is, and the buffer pool manager decides, oh, I need to free up space, ignoring that we have a free frame. It doesn't matter. We're going to somehow throw away throw away the frame and the first frame and throw away page 2. But then now, if the execution engine comes back and says, hey, I need page 2 again, the buffer pool manager can say, oh, I don't have it in memory. I got to go out to disk to get it. But it can now decide, OK, I'm going to put page 2 into this other frame and get back a pointer to the execution engine to where that is. So the idea here is that we're giving back pointers to pages so that the rest of the system can operate on them. But the rest of the system can't assume that the frame is going to be, that pointer is always going to be the same location. Right? It's always got to go through the buffer pool manager, because that's the final arbiter, the coordinator, to decide what's in memory and where can you find it in memory. So we can move things around as much as you want, and the rest of the system will work just fine. Right? Because the high level of the system is operating on record ID that produced page number 2. That's just something on disk. And then this thing says, OK, let me go get page 2. I know where to find it, and let me go hand you the pointer to it. OK? So this is the big picture of what we're trying to accomplish today. So I'm showing this sort of high-level example with, assuming we're getting tuples. There's going to be other parts of the database system that's going to also need memory pools, and they can rely on this buffer pool manager as well, but maybe not always. If any time you need to be able to swap things out to disk, like I'm trying to allocate a bunch of memory and I'm running out of space, like as I'm running a query, then you want that memory to also be backed by the buffer pool, because it knows how to move things out. So we'll see this later in the semester, but there's a bunch of different things we could want to use this for, like sorting and join buffers. Again, if I'm trying to build a hash table to do my join, but I want to be able to support a really big hash table and more memory than I have, then I can back up by a buffer pool, and it knows how to write things out to a temp space, maybe rather than a regular database file, like a scratch space or a swap space. Buffers for other doing maintenance operations, query caching, and so forth, right? Other things are going to need memory, and sometimes they'll be backed by disk, sometimes they're not. If you need to be able to spill to disk and still use that memory, then yes, you want to back by something that looks like a buffer pool. So what we're going to talk about today is sort of background on what the buffer pool manager is going to do for us, how we're actually going to implement one, the policies we're going to use for it. Then we'll talk about why you don't want to use mmap in your database system. But then we'll talk about how to handle disk I/O scheduling and replacement policies. And then this should be optimizations. We're going to finish off with a bunch of optimizations you can do to make your buffer pool manager better than what the OS can ever provide for you. Okay? And then we'll finish up with discussion real quickly on Project 1, which came out last week. So as I already said before, the buffer pool manager is basically something that's responsible for managing an array of memory of fixed size pages that it can hand out and reuse for different parts of the system that needs memory, right? And as I said, instead of what we're going to call sort of the placeholder location within that array of memory that we can reuse, we're going to call that a frame. And that's going to be the same size as a database page. Now, some systems can support different database page sizes per table or per table space, and they basically you have to have a buffer pool for each of those. Right? You're just carving up the amount of memory that the system is allowed to have. So the idea is pretty simple, that when some part of the system wants to access a page that's on disk, we first got to find a free frame that's available for us, and we're going to read that file from disk, or read it from whatever the remote storage, and we're going to copy that into our buffer pool. And then we can do this for as many pages as we want. And that the ordering of the data in memory does not have to match with the ordering of the data on disk. Just because it's page 1, page 2, page 3, in memory it won't be in that same order, because some frame was maybe free at a different time than another frame, and we just put things where we needed. The important thing to understand, though, is that even though this is a buffer, it's essentially a cache, it's going to be a write-back cache, meaning any writes that we're going to make to these pages when we need to operate them, we're going to make it to its in-memory representation first, and then at some later point, which we'll define in a few more slides, then that dirty page will then get written out and flushed out to disk. It's a bit more complicated than that, because there's actually additional metadata, like a log file we need to record, and we need to make sure that's written to disk before the page that got modified by that log record got written to disk. But that we'll cover later, right? So it's not a write-through cache. A write-through cache would be I write into the thing on memory and then immediately gets written out to disk, right? We don't want that for protection reasons, like durability reasons, because we don't know whether the operation that maybe wrote that page has actually fully been saved or committed, and we don't know whether we want those changes to be durable. But again, we'll cover that later in the semester. So in addition to keeping track of these frames, there's also going to be this additional data structure in our buffer pool manager called the page table that is essentially a mapping from a page ID to some location of where you can find that page in the memory of the buffer pool manager. Essentially a mapping from a page ID to a frame number, if it exists. And so there'll be some additional metadata we're going to maintain in our page table, or in the buffer pool manager, either within the page table or in separate data structures that we're going to use to keep track of what's going on with the memory that we've allocated and using in our frames in other parts of the system, right? Because we don't want to have someone say, I need page 2. We find a frame, put page 2 in there, and then someone else comes along, says, hey, I want page 3, and we take over that frame we just used for page 2 and put page 3 in there, because now two parts of the system is going to have a pointer to the same frame, but one guy's going to think it's page 2, one guy thinks it's going to be page 3, right? So we need some way to protect ourselves, protect our memory, and make sure people are getting back the data that they expect. So additional metadata we'll keep track as a dirty flag. Has the page been written by some part of the system? Therefore, we know that we just can't drop it when we need free memory. We need to write it back to the disk at some point. There'll be a pin or reference counter telling us how many threads or workers, whatever you want to call it, how many other parts of the system are holding pointers to those pages right now and could be accessing them. And then additional tracking metadata we'll see later on about the timestamps of maybe when things have got accessed, either from the last time or the last n number of times or k number of times. And we're going to use that additional information to keep track of what should be evicted. Or things like who accessed the page. Was it a query? Was it a background worker maintenance operation? Right? Was it in a transaction? Things like that. All right, so say a thread comes along and wants to access page 3. We look in the page table. Right? We'll use concurrential mechanisms, latching to get us in there to protect ourselves. But if we know that once we find page 3, and then we're the pointer back to whoever asked for this, we'll put the pin in there or increment the reference counter to keep track of, hey, there's somebody out there that's looking at page 3 right now in this frame, so don't try to evict it yet. And let's say someone comes along and wants to access another page that's not there. So in this case here, we got to take a latch on the page, the entry in the page table, because we want to say this thing's empty. We don't want anybody else trying to insert something while we're trying to insert something into it. So the latch is going to protect us. Then we take page 2, copy it into a free frame, update the metadata inside of this, this entry to say, here's now where page 2 is going to be found. Here's information about who accessed it and what timestamp. And then we can go ahead and release the latch on this entry in the page table, but we're going to want to pin it obviously first, because we make sure that nobody else then tries to overtake this page, this entry in the page table and put another page in there. All right? So this is a high level. This is what we're trying to do. Any questions? Yes?
When will a page be pinned?
This question is, when will a page be pinned?
Yeah.
It's like if I say, do you have page 2? And I get back, yes, here's the pointer to it. At that point, it's pinned, because I'm giving you a pointer to page 2, but it's really a pointer to somewhere, you know, in my frames.
So long as I'm holding the pointer, the page is still pinned.
The question is, as long as you're holding the pointer, the page is still pinned? Yes. Because what could happen? Someone could swap out what you're pointing to, because you're pointing to these locations in memory. If someone swaps out page 2 with page 4, but you still hold the pointer to it and you want there to be page 2, then you start reading things thinking it's page 2, and it'll read something else. Yes?
So is the execution engine's responsibility to tell back that I don't need this page anymore?
This question is the responsibility for the execution engine to come back to the buffer pool manager and say, I don't need this page anymore? Yes. Or whoever asked for this page, the contractor in the API is, here's the pointer, tell me when you're done. Which we can enforce because we're the one building the system. It's not like we're trying to deal with randos on the internet. Okay, so back here, I used the word latch. Depending on what that is. What's a latch? What's that? Mutex, yes, perfect. So there's this distinction between sort of the systems or operating systems world and databases. We're right, they're wrong. But what they would call a lock, we're going to call a latch. And as he said, it's typically going to be a mutex, right? We'll cover locks later on, but the reason why we can't use the word lock is because lock in the database world is meant to protect some higher level concept or logical entity within the database itself. So I can take a lock on a table, a lock on a tuple, a lock on an entry in an index. And there'll be some extra protection mechanisms that the data system is going to provide to make sure if there are deadlocks that you'll kill one of the threads or workers holding the lock to break the deadlock. Right? Like locks are dealing with the outside world, doing things on the database, and therefore we assume they're stupid, and we have to make sure that they don't lock up the whole system. A latch is going to be an internal protection mechanism that we as the database system developers, people building the system, that we're going to use to protect critical sections. And because we're getting paid a lot of money to build the system, that we're not going to be stupid about it, and therefore we're responsible for making sure that there's no deadlocks. Like there isn't going to be some thing floating above the clouds that can kill our deadlocks. It's through programmer discipline we make sure we don't do stupid things. Right? So then in this case, yes, you can use a low-level mutex. You can use the standard library mutex, which is really a few texts in Linux. We'll cover later. Most data systems don't want to use anything the operating system provides you. So we're going to roll our own mutexes ourselves, or roll our own latches. We'll cover how to do that later. But just when we say latch, again, think of like a mutex protecting critical sections, and therefore we got to make sure we don't shoot ourselves in the foot and have deadlocks. All right, the next question you may have is like, okay, well, what's the difference between a page table and a page directory? So remember, the page directory is this thing on disk that is going to be mapping from these page IDs to some page location in the database file or files, right? And anytime we make a change, we add more pages to our table or whatever, we have to update that page table. And the page directory. And if we restart, then we load the page directory back in. It needs to be synchronized with the actual files themselves. The page table is an ephemeral data structure that we're going to maintain in memory inside our buffer pool manager. That's going to be the mapping from the page IDs to the copy of the page existing in our buffer pool frames. So if we crash or stop the system and restart, the page table is going to be blown away, and we got to rebuild it, right? Because the second time around, we might be reading in different pages. Okay? All right, so now, if I just said what we're trying to do is maintain some internal data structures that's going to allow us to map page IDs to arbitrary locations in memory and give the illusion that we have more memory than we actually have, what does that sound like? Virtual memory, yes. So you're like, OK, well, why are we doing all this work? Why even bother doing project 1 if the OS can kind of already do this with virtual memory? Right? So how would you do this with the OS? So OS has this feature called memory mapping, or mmap. The basic idea is that you have some files on disk, you call mmap open on it, and that's going to literally map the contents of that file into memory for your application. And again, it's going to do this lazily. It's only, it's not going to bring all the contents of the file and bring it to memory, but it's going to give you some starting point and an end point based on the size. It says, OK, here's the regions of memory where you can access that data. And if you then try to access something that is not in memory yet, there'll be a page fault and it'll read it back in. Right? So again, it's going back to our database file like this. Right? We have this virtual memory thing here. Nothing's populated. My thread says I want to access page 1. Page 1 is not in physical memory. So there'll be a page fault while this thing goes. The OS copies that page, brings it into memory, and then updates the virtual memory to point to now your page. Right? Same thing. If I want to access page 3, copy it in, and we're done. Right? What happens now if I try to access another page? Well, I want to access page 2. I don't have any. The OS recognizes I don't have any more physical memory, so now hits a page fault and says, OK, the thing you want is in memory, so I got to decide which of these things I need to evict. And when it does that, it stalls your thread, stalls your process, because it's trying to be transparent to you to not know that, oh, the thing you wanted is in memory. It's just going to stop you from you running, deschedule you, fetch the thing you need, bring it into memory, and then once it's memory, then you get back the pointer to the thing you wanted, or do whatever it is that you wanted on it. Right? So the OS is completely hiding from you the mechanism to decide how to move things back and forth between disk and memory to give you, again, that illusion that you have more memory than maybe you actually do. All right? So if I'm saying it's going to pause your thread, well, that sucks, right? If I'm running my query, if I only have one thread in my system, then I can only run one query at a time. It'll be a long pause while it goes and fetches things out of memory and bring them into disk. So all right, well, what if I have multiple threads running at the same time? Won't that maybe hide some of the pauses because one thread could keep running while another one gets stalled? Does that solve all our problems? Well, I guess the opening slide said mmap's going to murder your database system, so you all think it's a bad idea. You don't maybe know why yet. Okay. So here's why it sucks. The first thing is that the operating system is free to flush any dirty page at once at any time. And I just said in the beginning, that's a bad idea, because if I write to a page, like an update query updates a page, if I'm updating multiple pages in that single query, I want to make sure that I make all the changes and have them all written out atomically before I say, yes, this operation has completed successfully. But as I said before, we can't guarantee that the hardware can write out more than a 4 kilobyte page at a time. So if I'm making a bunch of different pages dirty, and I may be still waiting to decide is this thing actually going to formally complete, the OS decides, all right, I need space. Let me start writing out let me start flushing your dirty pages. And then now if I crash and come back, I got to figure out what the hell the OS actually wrote before I crashed. And I don't know what it wrote because it did it all for me underneath the covers. So that's terrible. We've already talked about the stalls, right? Since the database system doesn't know what pages are in memory because the OS is managing all that for us, you can't look in the page table and say in the OS and say what's actually in memory or not. That at any time you could try to touch something and then you end up stalling. So how do you get around that? Well, you could have something that occasionally tickles pages in a separate thread. So if it stalls, no big deal. And then that way when your query tries to go and touch it or touch the page, it doesn't end up get stalling. But now you're building a bunch of extra infrastructure to overcome this problem with the operating system, and you end up building a lot of infrastructure you would need anyway to have a buffer pool manager. And furthermore, how are you going to know what pages to tickle? Tickle's not a bad word, but you know what I mean. How do you know what pages you want to touch before you need to touch them if you haven't run the query yet? So that sucks. What happens if there's an error, right? Do you get an exception? Do you get like an error number? No. You get an interrupt. How do you handle interrupt in your program? Interrupt handler. Where do you put that? Everywhere, right? Because now at any time, at any part of the system that you're accessing memory, but it's backed by mmap, you have to also include the interrupt handler, because all of a sudden you may try to tell something and you get a SIG bus, and you got to decide what to do with that error. Right? At least if you use like the libc or POSIX API to do fread, fwrite, you'll get back an error number. It's going to lie to you sometimes, we'll cover later on, but at least now it's a single location where I know I'm going to be accessing something on disk, I bring it to memory. Now the rest of my system can operate on those pages in memory, and I don't worry about them touching something that somehow magically got swapped out or some issue happened that the OS is hiding from me. And then we're not really going to get to performance issues, but take my word on this, it's going to be slow. Because how does the OS maintain that mapping? They basically have their own version of a page table. How are they going to protect it? With mutexes. Are they going to be good mutexes? No, it's going to be the libc futex one, which there's better ones out there, even though Linus disagrees, right? So now all the things we're trying to, we'll see these optimization later on, but all the things we can do to reduce the contention on our page table and being smart about what we're evicting and why we're evicting it and when we're evicting it, all that gets thrown out the door because the OS is doing everything for us. Yes?
So for the problem 3, is the problem that there will be too much exception, or is that
There's no exceptions. It's interrupts.
Oh, yeah, interrupt. Sorry.
Yes.
Is a problem that there will be too much interrupt, or is that the information is not enough?
Its question is, what's the problem with the interrupts? Because the problem is that it's any time I touch something in memory that's backed by the mmap, I could get an interrupt.
So it's too much.
It's like, so you basically need to duplicate error handling code all over the system. Versus like, if the error is going to occur when I read something, right, there'll be one location in the disk scheduler that we're going to manage ourselves to say, okay, now I'm doing the fread or the read, go get my data, and I can check at that moment of reading, do I get an error or not? So the blast radius of where that error can break is just located in the part that does the I/O. Versus like, I'm touching memory that's magically backed by mmap files, I have to have error handling anywhere, because any operation on that memory could throw an interrupt, could hit an interrupt. All right, so there's some ways to avoid some of these problems, but again, as I'm saying, it starts to smell and look like a buffer manager you're going to build in Project 1. So you can use the madvise function. You can basically give OS hints about how you're going to read certain pages. You're going to read these things sequentially. You're going to read these things in random. You can call mlock on it. You basically tell the OS that it can't, some memory ranges can't be paged out. Now, you can't guarantee it's not going to be written out, because the OS can still flush out dirty pages for you. Mlock doesn't protect you from that. It just says, I can't swap it out. And then you can call msync, which would be equivalent to fsync, would be tell it to flush out memory ranges out the disk, right? So there's all these tricks you can do to try to contort mmap to do what we want in our buffer manager. But at the end of the day, you end up building something that looks like Project 1. And it's going to be even crappier, because you still have the core mechanism of reading things in and out from disk managed by the OS instead of the database system, which is always going to be in a better position and know more about how the data is going to be used than the OS could ever be. Right? So there's been a lot of systems that start off building mmap, or basing their system based on mmap. And surprising number over the years that we felt compelled to actually write papers about why this was a terrible idea. So there's two categories here. There's all the systems that make full usage of mmap, and then the systems that maybe started off using full mmap and then switched to partial usage and eventually got rid of it. So I actually found out today from the Weaviate guy, they started off using mmap, and then they realized, as I was saying, that it was a bad idea, so they got rid of it. So all these other people have made the arduous journey of starting with mmap because it's quick and easy and gives them some basic functionality that they would want, and then it turns out it's a terrible for all the reasons I talked about before. Or in some cases, it's also terrible if you're running in the cloud and you want to be able to have observability in the performance usage or the resource usage of your data system. mmap hides a lot of crap from you. So I always like to talk about MongoDB. MongoDB is a very flexible data system, despite some of the hiccups they had over the years. And one of the hiccups was that when they first came out, they were based entirely on mmap. And they raised a lot of money. They had a lot of customers. They had a lot of top engineers. And even after all those engineering resources that were available to it, they end up throwing away the mmap engine and switch over to WireTiger, which is based on the buffer pool manager that you're going to build in Project 1. So if MongoDB couldn't figure it out, then what hope does any random Joe Schmo startup have without those resources? SQLite has it, but they have it for portability reasons, and it's not turned on by default. Right? Systems like Elastic, they're primarily read-only, serving read-only workloads. So same with MongoDB. So mmap might be OK in that case. Right? You won't have maybe the safety issues that other systems have. LMDB is the exact opposite of me. I'm telling you never use mmap. He's telling you use mmap for everything. He loves it, right? And he emails a bunch of the other database systems and tell them why they're doing it wrong and they should be using mmap. And he's the opposite of me. Weaviate, they still have some mmap in it, so they're probably really down here, but they're eventually going to get rid of it, right? All right, so again, the thing to reemphasize over and over again, the data system is always going to do a better job than any other part, than the operating system could ever do, because it knows what the queries want to do, what data has been modified, what's coming up, and can always make the best decision, right? The OS is not going to be our friend. We need it to survive, but we don't want to rely on anything that it's going to provide for us, especially managing memory. And so, as I said, we wrote a paper on this a few years ago. Never use mmap in your database, and we discussed all these issues. And then there's also a short little video that's on YouTube you can watch that basically shows the challenges and trials and tribulations of using mmap. We thought this would be a way to, again, evangelize our ideas. And he buys an mmap buffer pool manager from a shady guy in the streets and then puts it in his database and then realizes it falls apart. All right, but anyway, that's all available online. OK. So if we're going to read things into memory, into our buffer pool manager, at some point we're going to run out of memory, and therefore we have to start making decisions of what to evict to free up space so we can use it for new pages, right? But there's a bunch of things we need to consider in whatever algorithm we're going to use to decide how we want to evict things, because we don't want to be slow like the OS. We want to take advantage of all the things we can extrapolate from the workload and from the queries and the data to come along and make a better decision. So this is sometimes called the buffer replacement policies or cache replacement policies, right? They have a bunch of names. This is like one of the classic problems in CS, right? One of the oldest problems, and everyone has a paper in this space. I think we have 2 of them. I forget. So we obviously want to make sure that anything, when we decide what pages to evict, we want to pick the correct ones. Right? We don't want to pick the page that's most likely to be used next by the query, because then we'll be thrashing back and forth at disk. We need to make sure that we can quickly determine what pages to evict quickly as possible. Right? That means we don't want an NP complete algorithm to find the most optimal page to evict, because then if our page eviction algorithm takes 100 milliseconds but only takes 10 milliseconds to read the page, that's not a good trade-off. We need to make sure that we don't evict anything that is not durable yet, meaning we don't want things to if we haven't written out the log record that corresponds to the page, or to the modification of a page, we can't write that page out until the log record is written out for safety reasons. And then for the amount of metadata we need to keep track of for our pages, we want to minimize that as possible, because we don't want to use a lot of memory to keep track of all this extra metadata, because we could be using that memory for storing pages themselves. So I will say this is one of the things that's going to, again, differentiate the open source systems between the high-end, expensive enterprise systems, like Oracle, SQL Server, DB2, Teradata, and so forth. They have spent millions and millions of dollars, hundreds of hours of engineering to try to optimize this thing. And Postgres and those other guys are just simply not going to be able to compete. Right? The enterprise system is going to have way more bells and whistles than what is available in the open source ones. The problem is also, too, sometimes they don't always talk about what they're actually doing. You can kind of glean it from reading the documentation, but there's a lot of different options that are available in the enterprise system, and we'll touch on a little bit of those as we go along. So the most common buffer pool replacement policy is going to be what algorithm? It's like intro CS. LRU, least recently used, right? And it's pretty straightforward, and it works reasonably well. So the idea is that for every single page, we're just keep track of when was it last accessed. Right? Again, the execution engine has to go to the buffer manager and say, give me page 2 to get back the pointer to it. And at that point, we can record, OK, what is the timestamp, either the wall clock time or a logical counter that says, here's the time when this thing was accessed. And then so we can use a bunch of different data structures to keep the pages in sorted order, like a linked list or a B+ tree or a trie or whatever. And we can use that to determine very quickly, when it comes time to evict something, which one was the least recently used. Right? So simple example, query 1 comes along, touches page 1. Page 1 is in the middle here. Right? And so now we're just going to move it to the head of the list. Right? And then when it comes time to evict something, since page 2 is at the tail of the list, that's the one we're going to choose to evict. Right? So this is going to keep sort of an exact ordering, again, based on the access timestamp. There's a more simplified version of this where you actually approximate the ordering. You may not know exactly whether one thing was accessed before another one, in the way LRU does, but we reduce the amount of overhead we have to maintaining these timestamps by just saying has been accessed recently enough. And the algorithm used to do this is called clock. Who here has heard of clock before? Small number. OK. This is actually what Linux uses. They use a multi-hand clock, but the idea is basically the same. So this is going to be an approximation of LRU, where instead of recording a timestamp, all we're going to do is keep track of 1 bit per page that says, has this thing been accessed since the last time I checked? And you're going to check every so often, every time you got to evict something. And if the bit is set to 1, then you know it's been accessed, and you can reset it to 0. If the bit's 0, then you know since the last time you checked, it hasn't been accessed. And so you basically map the pages in this sort of circular order like a clock, and everyone has their own ref bit. And anytime a page is accessed, you just set the bit to 1. So now when it comes time to evict something, I got to find a frame to free. So I start at some location. It can be random. It could always be the same spot, or pick up where you left off. Doesn't matter, because eventually it all rounds out. So I go to page 1. Has this thing been accessed the last time I checked? The ref bit is set to 1, so yes. So therefore I shouldn't evict it, but I'll set its ref bit to 0. Clock sweeps around, looks at this page now. Ref bit is 0. I know hasn't been accessed since the last time I checked, so I can go ahead and blow it away. And I can fill it in with a new page and set its ref bit to 0. Right? I just keep going around and do the same thing over and again, and then maybe the clock starts back over at the top. This guy hasn't been accessed. We set it to 0. Yes?
The reason why we loaded page 5 to replace page 2, we set the ref bit to 0 instead of 1. 0 is like mostly recently loaded.
So the question is, back here when I swapped out evicted page 2, I brought in page 5. I set its ref bit to 0 instead of 1. Well, the idea here is that I brought it in, but I have no history about whether it's going to be accessed again, so I'm going to set it to 0. Because maybe I had to bring it in. I serviced the request that needed it, right? So that's fine. I'm able to do that, because again, we're still maintaining the pins on these things. But I set it to 0. So that way, if I come back again, if it was a one-shot, one-time read, then it'll get evicted. If someone else really needed it, then its bit will be set to 1, and therefore it won't be evicted. So it all sort of just works out. Right? Yes?
Do we just delete a random page if they are all set to
Its question is, would you delete a random page if they're all set to 0? So you whatever. Sorry. Its question: if they're all set to 1, what do you do? Well, when you check and it's set to 1, then you set it to 0. You come back around, and then it's been evicted. At that point, if you're stuck in an infinite loop, you basically have a counter set how many times I've looped around. And then if you just can't evict anything because they're all pinned, they're all set to 1, then you reject the query. You say, I can't run. Or you send an out-of-memory error or something like that. But at that point, like, queries would run super, super slow. So like the human or some operator would know this thing's overloaded and do something else to try to mitigate it. All right. So LRU and clock are nice. They're pretty simple to implement. But they're going to be susceptible to a problem that we have to face in database systems called sequential flooding. And the idea here is that if we have a query that comes along and it wants to do a sequential scan on an entire table, meaning it's going to read every single page in that table, either once or multiple times, but if, in the case it's doing a join, then this is basically going to wreck our buffer pool and all this metadata we're tracking for it to keep track of how things are being used. Because now everything's going to look like it was just recently accessed, and it's going to throw away things that maybe were really hot we definitely want to keep in, but because we're only going by what was most recently accessed, they'll get the things that we should have kept in we're going to end up throwing away. So in OLAP workloads or analytical queries, it's actually sometimes the most recently used page is the one you want to evict. Because again, I'm scanning through. Say I'm scanning through once, I bring the page in, I read it, then I'm never going to read that page again in that same query, and maybe it's a one-off thing that nobody wants to read. So that's actually what I want to evict, right? The most recently used, not the least recently used. All right, and the problem here is that LRU and clock, since they're basically storing a small amount of information, like when was it last accessed? It doesn't tell you how many times it's accessed in the past. We're not in a good position to make decisions about should we actually keep this thing in memory or not. So just again, show the example. Say I have this query here. It's doing a primary key lookup where ID equals 1. This is very common, right, in OLTP workloads, looking up single records. And say that's in page 0. We have a miss. We bring it into our buffer pool in this frame. And we service the query, and we're done. But now someone comes along with compute an average value across the entire table. So that's just going to scan through and read every page one by one. Then at some point, we're going to run out of free frames, and it's have to decide what I want to evict. Well, based on the scan, page 0 was the least recently used, so I'm going to go ahead and evict this, right, to bring in now page 3. But now, as I was saying before, if this query shows up, the same query shows up again once it accesses that same page, because it's a hot record. A bunch of queries keep wanting to read over and over, like it's Taylor Swift's Twitter account or whatever she's using. Instagram, sorry. All right, I gotta bleep that. All right, so what's that? Yes. All right, so anyway, so this query keeps executed over and over again. Page 0 should be kept in memory, but because we're only keeping track of what's least recently used, it's going to get evicted, and now we have never have to go back to disk again and get it, right? So that sucks. So the way to overcome this is a simple technique called LRUK. And it comes from a paper from the same guy that invented log structure merge trees that we talked about a few lectures ago in the 1990s. And the idea here is that we just keep a little extra metadata to keep track of the last number of, for some K references of the timestamps of when the page was accessed before. And then when it was come time to decide what to evict, you look at this history and decide which one has the longest interval from the last time it was accessed from one access to the next, and that's the one you end up deciding to evict. So what you end up nicely balancing is things that are recently accessed over and over again in quick succession, and the number of times that it has been accessed. There's some additional tricks you can do that SQL Server does that Postgres doesn't do, where they actually keep track of, is this page being accessed repeatedly within the same transaction? Like, for whatever reason, I go get Andy's order record, I do something, then update Andy's order record. Well, that, if you're just doing regular LRUK, that would look like this page was accessed twice, but it's really in the same transaction, so you can kind of technically say it's only been accessed once, right? So SQL Server can distinguish in what context a page is being accessed and add that to its additional metadata to keep track of these previous entries, right? Another problem you can have is with cold starts, right? If I stop the system and come back up, now I have no metadata about when things are accessed. So sometimes I sort that out to disk. Or I can maintain things like, if I've recently evicted something, I don't want to throw away anything I'm having in that metadata about how many times it's accessed. Maybe I had to temporarily write it out because I had to do some big operation and I needed space. But then when I bring it back in, I don't want to learn from scratch all over again how often it's being accessed. I'll maybe maintain a small cache and say, here's this metadata, here's the metadata when it was accessed, when it was in memory before. And that way I can have my algorithm converge pretty quickly. So this is actually what Postgres does. There's a mailing list post from like 2002. Again, open source system, so everything's public. Where someone says, hey, we found this paper. This seems like a good idea. We should do this. And they did it. Right? This is what Postgres does. It's exactly what the paper does. MySQL does something a little bit different. They have a technique they call approximate LRUK. And the idea here is that it's still a single linked list, if you will, of the ordering of which pages are accessed. But now they're going to actually have two entry points or two heads for the LRU list, one for a young section and one for an old section, right? And the idea here is now when someone accesses a page, it gets added to the buffer pool, and we need to keep track of when it was accessed. Instead of just adding it to the beginning of the LRU chain, we'll add it to the first time it's accessed to the old one. So think of this like, hey, yeah, we know we needed you, but I'm not going to immediately keep you around for a really long time. If I put you in the beginning of the entire list, I'll put you in this middle point here, because then if it does need to be accessed, then I'll eventually get upgraded here, right? So in this case here, page 1 is going to get put here. We evict the last page. Everything slides over. If I now access page 1 again, I'm going to pull it out of this part here and put it now to the front of the head, the young section, right? So the idea is, again, it's like LRU with k equals 2, where like I'll keep track of like the last time I was accessed, am I in the old section or the new section? And then if I'm in the old section, then I'll get promoted to the young section. So I'm even less likely to get evicted the next time around. And eventually it gets washed out, because if it never gets accessed again, then it just moves back down here, and then it'll get evicted. All right, MySQL does this because it's easier than what Postgres does and SQL Server does. It's less metadata. It's like an easy extension to LRU. So there's a bunch of other things we can keep track of to decide when to evict things. We can do this on a per query basis, or we can do it globally for the system. We actually can be more fine-grained. In some systems, we can do it on a per table basis, or even per index, per table space, right? So in the idea of a global eviction policy would be, across all the queries running my system, I'll decide which page is least recently accessed. But in some cases, what I want to do is have a small region of my buffer pool be dedicated to one particular query. And then when I want to decide something to evict, I'm just evicting things localized for that one query that doesn't affect the rest of the system. So what I made this. So Postgres does this. So when you do sequential scan on Postgres, they'll allocate some portion of the buffer pool as a ring buffer for that one query. And then now if I'm doing sequential scan and I'm bringing in pages one by one, if I run out of space in this ring buffer region, instead of just evicting whatever the global least recently used page for my entire buffer pool manager, I'll just take whatever the least recently used page was for this ring buffer, this portion of memory. So now I'm ripping through pages, and I'm throwing things out and evicting things based on what I need, and it doesn't pollute the sort of the global eviction policy for the rest of the system. Right? And this is like, per query, they'll give you like 256 kilobytes in the buffer pool. So like 32 pages, because it's 8 kilobytes a page. So it's not a lot of memory, but at least it's enough to prevent pollution from the rest of the system. So now if I do a sequential scan in Postgres, I evict things based on in this sort of this sliced out region. It's still accessible to the other parts of the system, the other queries, because I need to know, for a given page number, what frame is it located in. But when it comes time to evict, if nobody else actually needs it, then I can go ahead and evict something that the least recently page I read. Another trick we can do is pass along priority hints to the buffer manager about how a query is going to access a page. And then now the replacement policy can use that in its decision to decide whether to evict something or not. So you can almost think of like a hint as like a light pin to say, hey, this thing is important. I'm probably going to need it a lot, but I'm not really accessing it right now. So if you got to evict it, sure, you can evict it, but try not to. So this will be important for things if you have indexes, right? Which we'll cover, B+ trees and tree data structures next week. But say I have a query, this is not real SQL, but I just have this auto-incrementing value, like a serial key, where the value I'm going to assert is +1, whatever the previous one is, right? So what's that going to look like if I insert this to a B+ tree that's sorted based on the ID? Well, all my inserts are going to end up on this side of the tree, and I keep extending the tree out in that direction. So what's the very first thing I'm going to access anytime I do an insert in a tree? The root, and then the path down along the, to your right side of the tree. So I can give a hint to the database system that says, hey, these pages are kind of important, so make sure you don't evict these if you can't, if you don't have to. Certainly the root page is important because that's the thing I'm going to hit over and over again. Now, you can say, oh, LRUK would keep track of this thing being hot and being used all over again, and therefore I won't evict it, but it'll, just to be sure, you can pass along a hint. Right? Of another query like this, again, they're going to go down maybe any random location, but if I can give a hint to say keep the root in memory, then that'll make things better for me. All right, so again, the buffer overracing policy is all about deciding which page we should evict from a frame so we can reuse it for another page. So I've already said a couple of times that, like, okay, well, we're giving a pointer out to the execution engine, and it can do whatever it wants with it. It can decide it's going to update the contents of that page, right? You can insert a new entry into a new slot, update something, whatever. So if a page is not dirty, then that's great for us when it comes time to run eviction, because now I say, I don't need this page anymore. I'm just going to, you don't have to zero it out. You just copy over whatever the new page you want to put it, copy it over the old one, because they're always going to be the same size, and you're not going to see any data from the previous page. Right? That's the fast path. You basically just can virtually drop a page from its frame and reuse it right away. But if it's dirty, if it has been written, then I just can't overwrite it. All right, I got to make sure that the dirty page is written out the disk and is safe on disk before I can reuse that frame. So now in your eviction policy, there's this trade-off between the fast path of, okay, I can just drop the frame and reuse it, versus I have to write this dirty page out the disk. But it may be the case that all the frames that are clean are things I definitely do not want to evict. And what I really want to do is evict a dirty page, because I wrote something and I'm never going to read it again. I want to write that back out. Right? So there's this trade-off between deciding when to do the fast path, just dropping something, versus having to write something out, because the thing I want to write out probably could be something I could never have to come back and be done with it. Right? So it's not like there's like the side buffer where we can say, okay, this page is dirty, so let me put in this other buffer here, and then that way I can reuse the frame, and then eventually I'll write out that other the dirty page. Because if I had that, then like I should just be using that for my buffer pool anyway. Like it's memory I could be using for other things. So the way we can avoid this problem, or try to mitigate this problem, it doesn't, you can't avoid it, it doesn't go away. You can have what is called a background writer, where every so often the data system has some worker comes along, looks in your buffer pool, looks at the frames, finds whatever's dirty, and then flushes and writes it out to disk. The page still exists in memory because we're not evicting things there. They're just kind of, we're eagerly writing things out to disk, assuming at some point it's going to get evicted, and we don't have to block why that happens. That's going to write out a dirty page, and then once it's safe, then we flip the dirty bit, the dirty flag in the page, and now it's clean. So now when the eviction policy runs, it says, oh, this page is clean, therefore I can go ahead and evict it. This is sort of what the OS was trying to do for us in mmap. Right? It had this background writer where it was writing out pages to kind of make sure that, to essentially do the same thing, drop the ones that aren't dirty. But again, because the OS doesn't know anything about transactions or all the other stuff we're doing in the rest of their system, it doesn't know that it shouldn't be allowed to write out a page because something else hasn't been written yet. Again, we'll talk about the write-ahead log later on, but again, think of that as just like the record of the information about what was changed in what location, and that if we end up have to crash and come back, we can look at that log and recover any pages that have been dirtied and maybe haven't written out the disk yet. The OS doesn't know anything about that. You can't tell it, don't flush it until this thing's been flushed. In our system, we can enforce that. So there's different systems have different policies you can set for when the background writer should run. They can be very aggressive and flush out dirty pages over and over again, but now you're spending resources writing out dirty pages instead of using those resources to run queries. On the flip side, if you never had the background writer run, then any time you need to evict something, now the query is blocked because you have to flush out dirty pages. So there's not any one magical answer I can give you, say this is how you want to always set these things. Different systems do different things and expose different things to you. And this is, again, where the secret sauce comes in for the enterprise guys, where they can be a bit more sophisticated than the open source ones about when the background writer runs and what it evicts. A simple trick would be, I run my, when I have to decide what dirty pages to write out, I actually piggyback off the eviction policy, the buffer pool replacement policy, find out what dirty pages are more likely to be evicted very soon, and flush those guys out first, instead of flushing out any random page. Okay? All right, so now, I got to read and write from disk. What does that look like? How are we going to do this? So the hardware and the operating system is going to have their own bunch of tricks that they're going to maintain or employ to maximize the bandwidth they can get out of the hardware by reordering and batching I/O requests. Right? The reason why modern like M2 drives and NVMe drives are so fast is that you can do a lot of parallel operations on them and get really good throughput out of them. But so that means, of course, if you do a stupid thing like have one thread do one read-write at a time, the system is going to be super slow, even though you might be running on the most modern hardware. So we're going to try to batch things together, but the OS, again, doesn't know the relationship between these I/O requests and doesn't know anything about whether one request is more important than another, because it just sees read these files for me, or read these blocks for me, and doesn't know whether one should be serviced before another. You can set I/O priority in Linux, right, to say like make sure that these requests happen before another one, but you can only do that on a per process level. You can't do this on an individual request level. So for this reason, most data systems are going to maintain their own disk manager, disk scheduler, where they're given a bunch of the read-write requests from the buffer pool manager and other parts of the system, and they decide in what order should they actually apply them. So most database systems are going to tell you to turn off any additional scheduling that OS provides for you, Linux provides for you, and either use like the simple deadline or the FIFO scheduler. And there's manuals that saying, hey, you're going to run MySQL, run Oracle. Make sure you turn off all these features in the OS because it's going to cause problems for us. Priorities also don't work either too. As soon as you call fsync, we'll cover in a second, fsync basically just destroys all the priorities because the OS says, okay, yes, we do fsync. That's the most important thing. Let me flush this right away, which may not be always what you want. So again, the data system is going to maintain its own internal queue to keep track of the read-write requests for the entire system. And then it can decide how to order them and how to service them based on the context of how they're being used. Right? Is it like a mission-critical query that has a higher priority? Well, maybe that should get serviced first before some background worker job that's cleaning things up. Right? Or if I'm reading, if I know that something, if I have two queries accessing two different tables, and this other query is holding a lot of locks on the system, on a lot of tuples, and therefore I want to free up those locks as soon as possible, I maybe want to service that one first before this other query. Because if I get that first query done first, it'll release those locks and then unblocks a bunch of other queries. Right? There's a bunch of tricks like that that we can do in our scheduling policy to decide how to prioritize things. We're not going to talk about asynchronous I/O in this class, but there's there's a whole other way to implement disk managers using IOU ring, if you're familiar with that, or asynchronous I/O. Basically using coroutines. Instead of having your thread make a request and block until it's actually serviced, you basically can say, I need this block of data, notify me as a promise or something like that when it's actually available for me. And Linux has a nice thing called IOU ring that has basically a buffer that allows you to fill requests in and notify them. So you could say, if I'm scanning through a table in a query, and I know I need pages 1, 2, 3, I could check the buffer manager. I know I have pages 1 and 3 in memory, but I don't have 2. So I send my request for page 2, let that be serviced asynchronously, do whatever processing I want on page 1 and 3, and then when page 2 is available for me, then I start processing that. So there's things like that you can do if you control everything in your data system. IU ring is still pretty new, so not a lot of systems take advantage of that. So again, the OS doesn't know anything about what our queries want, and it's always going to get in the way, and in some cases, it's actually going to lie to us about when we start, when we start to interact with the hardware. The OS can tell us things that aren't actually true. So if you call fread in your database system, against the OS's file system, like against the POSIX API, well, what happens? That hits the file system running inside the kernel. The kernel says, OK, you want to read this block of data or page of data from disk. It's actually going to first check the OS page cache. Everyone know what that is? It's basically a buffer manager sitting in the OS for pages that are on disk. So it's going to have its own region of memory that it's going to maintain cache pages in memory. Checks, you're trying to read this file in this offset, checks the page cache. If it's in there, then it services your request right there. Otherwise, then it goes down to the hardware and then fetches it, puts it in the OS page cache, then makes a copy for you, and then gives it back into your database system. So essentially, for every fread, if you're using the OS page cache, there's 2 copies of the page. There's one in user space for you, the database system, and then one down in the kernel. And that sucks, right? Now we're doubling the amount of memory we're using in our system to read files from disk. And so for this reason, most database systems will use what is called direct I/O, or you pass the ODirect flag when you call fopen. And this can tell the operating system to bypass its page cache. Now any freads, any read operations go directly down through the file system down to the hardware, and you get back the blocks of data that way. And now it's only one copy from the kernel into you, right? Avoids redundant copies. Doesn't the OS page cache is going to have its own eviction policies that we don't want to deal with. And now we want to have complete control over any operations we're doing on disk. There's one famous data system that relies on the OS page cache, and it's a terrible idea. I'm going to take a guess who it is. You said what? LMDB? They're using MF. That's a whole different. They have other problems. It's Postgres. Postgres famously relies on the OS page cache. If you go read the documentation of Postgres, we don't have time to do a demo, maybe do this next class, but you can see how Postgres uses the OS page cache, and it tells you when you allocate memory to Postgres, they tell you only use 25% of the amount of memory that's available in the system. Every other database system says use 80% of memory that's available to you for the buffer pool, right? Let the OS have 20% or whatever minimum it needs to survive. The data system wants to take the rest. Postgres says only use 25-30%, because they want the rest of the memory to use for the page cache in the OS, right? I think this is some remnant leftover thing from the 1980s when they first designed it.
Is the amount of memory the same?
Is the question, is the amount of memory the same? What do you mean, amount of memory of what?
Provided by Postgres and provided by other DBMS.
This question is the amount of memory provided by Postgres the same? Well, no, you're saying, like, when you set a buffer pool manager size, you're telling when the system boots up, use this amount of memory. Use 10 gigs of memory, right? And that's how much they're going to roughly allocate for the buffer pool manager. So Postgres, say your box has 100 gigs of RAM, right? Postgres says, hey, use 25 gigs. Everybody else is going to tell you use 80 gigs, because they want the extra memory to use for the OS page cache, right? So again, that may mean something like that Postgres could evict something from the buffer pool, and it still exists in the OS page cache. They realize this is a bad idea, and they're trying to get off it. And there's actually a blog article, it's on LinkedIn from a few months ago from somebody working on Postgres at Microsoft. And it's hard to see the screenshot. But basically, there's a new experimental feature that turns off the OS page cache and lets Postgres use direct I/O. There's a bunch of things they want to fix for I/O in Postgres. And this is one of them that's coming out in later versions. Again, because you don't want to let the operating system manage anything for us. We want to do everything ourselves. All right, let's do a quick quiz. If you've taken an OS class or before, let's see how this goes. So if our beautiful database system calls fwrite, what happens? We have some page that's in memory. We call fwrite, and we want to write it out to a file. What happens? It gets copied down into the kernel, and the kernel then buffers it and writes it out to the device eventually, right? Right, it's going to be in some buffer layer going down. All right, well, that sucks, because if I crash now, my fwrite that I just did, I could lose data. So what I need to do, I got to call fsync. What does fsync do? It says immediately flush. Who's telling what to do what? What's that? The database system telling the OS, and the OS tells who? The hardware. So the database system is beautiful. It tells the operating system, hey, make sure that thing I want you to write is actually written to disk, the actual device. So then the OS then makes the call down to the hardware device to say, hey, make sure this thing's actually getting flushed. Now the hardware can lie too, because it could have batteries down there, right, that can keep things in its own little buffer in memory. So that says, yeah, I have sync, no problem. And then eventually it'll actually get written out. So like there's a small chance if if the battery breaks, you might lose your data. But the idea is that you call fsync, and by the time you get a response back, because it's a blocking call, it's a syscall, you know your thing's been written to disk. All right, well, what happens if fsync fails? What happens? So you call fsync and you get back an error number. So what does that mean? Did my write succeed?
No, but you don't know if it's partially succeeded or not.
No, but you don't know what, sorry?
You don't know if it's partially succeeded or completely you didn't write it.
Yeah, she says you don't know whether it's partially conceded or partially succeeded or nothing been written, right? Well, Linux would mark your dirty pages as clean. So fsync would fail, and then they would mark the dirty pages clean. So you would get back the error number and say, yeah, your fsync failed. But then if you call fsync again, Linux has already marked the pages as clean, so it would come back and say, yep, your fsync succeeded, right? So in a bunch of different database systems, they would call fsync in a while loop, right? Call fsync. If it fails, just try again. And because now Linux was marking these pages as clean, you come back the second time, you call fsync, and it says, yep, the OS says, yep, it succeeded. But it's lying to you, right? So again, don't do this. So now you say, well, why would Linux do this? Why would they lie to you and tell you the page table is actually clean? Because the kernel developers are worried about somebody plugging in a USB thumb drive, right, calling fsync on that after it's been pulled out, and then it never gets plugged back in. So now their page table has a bunch of these dirty pages from the USB drive that's never going to show up ever again, and they need a way to clean up the page table. So they said, oh, just mark them as clean. That's fine, right? But database systems are not running off of USB thumb drives. At least they shouldn't be. So this is actually the worst thing for us. So this is actually a big scandal that came out in 2018. It's not very long ago. This is actually a bug in a bunch of database systems for 20 years. Right? It's not just Postgres hit this problem. Postgres, MySQL, MongoDB, and a bunch of others were basically doing the same thing. Actually, I should have tried on ChatGPT. If you asked ChatGPT to write code for this, probably could put it on a file on a while loop, right? And so what happened was some guy shows up on the mailing list and says, hey, Postgres lost so much of data for me, but I didn't have a kernel panic and I didn't have any error numbers. And eventually someone dug down into it and realized, oh yeah, fsync is actually lying to us for 20 years, right? This is why the operating system is not our friend. We should never trust it, and we can do everything as much as possible try to avoid relying on it to tell us what should be doing, right? Because of problems like this. Okay. All right. So we have 10 minutes left. I want to blaze through a bunch of optimizations you can do in your buffer manager to make it faster. Some of these you could employ potentially for project 1 to boost your ranking on the leaderboard, but not necessarily. And again, these are the things that we can do that the operating system cannot do for us because it just doesn't know what our queries are wanting to do and what our database actually looks like, right? Again, I would say the first one's probably going to be the biggest win and easiest thing to do to multiple buffer managers. The other ones are more complicated and they have various trade-offs of when it works and doesn't work, and the engineering difficulties. But the first one's pretty easy. You probably want to be doing this. I forget whether in this year's iteration of Project 1 whether it's possible to do this. But all right, so the first optimization is we don't necessarily have to have one giant buffer pool manager for the entire database system itself. Right? You can have multiple buffer pool instances. You can have one per table, one per index, one per table space, or different logical databases on the same database instance. And the basic idea is that we're just partitioning memory across the different buffer pool managers. And that'll reduce the latch contention we have inside the data structures, because now different workers will be accessing different buffer pool managers, updating their own LRUK information, and everything's sort of spread out and reduces contention. So now you say, okay, how do I keep track of what page is in what buffer pool manager? Well, there's two basic approaches. One, you can rely on the object ID that's part of the record ID that we talked about before. Remember when I showed in SQL Server, we ran that function on the record ID, and it split up, showed me there's the file number, the object ID, and the record, the page number, and the slot number. Right? We could use that additional metadata to tell us what buffer pool instance we should be going to. Right? So say like it's a high-level operation like get record 123. Obviously this is not SQL. So we take this record 123, we get back, convert it into what the logical constructs of the record ID represent, and then we just take this record ID, and we have some mapping table that tells us what buffer pool manager we could go to. And again, on the enterprise systems, you can actually specify on each buffer pool instance, like what page size are they using, right? What LRUK algorithm are they using, right? How to prioritize one page access over another, right? You can specify, you can set those protocols directly on each buffer pool and have them managed separately. The more easier approach is just do simple hashing with round robin selection of a buffer pool to use. This is essentially what MySQL does, right? So if we're given record ID, you hash it mod n, where n is the number of buffer pool managers you have, because you have to define it ahead of time how many you want, and that just tells you where to go, right? And no matter what thread accesses the same record ID, it's always guaranteed to go to the same page, right? Because a page can't exist in different multiple buffer pools at the same time, because the coordinate across those things would be impossible or difficult. The next optimization we can do is prefetching, or just sort of obvious thing you'd want to do if you're fetching things from disk. So because SQL is declarative, we know what the query wants to do. Therefore, we can try to identify ahead of time, based on the query plan, what pages it's going to access in the future, and go ahead and prefetch them. So for sequential scan, that's pretty easy, right? I'm accessing page 0, I bring that in my buffer pool, but then now I know I'm going to scan down and read page 1, 2, 3, 4. So when I go fetch page 1, I'll also maybe go fetch page 2 and 3 as well, and bring those in. So that now when I come along and continue processing, the page I need is just there for me. Right? Because my diagrams just look like I'm accessing page 2 and then immediately access page 3 and page 4. There's a little bit of processing going on, right? That I'm not showing here up in the execution engine. Like I'm gonna look at the data, interpret the bytes, run some predicate on it, maybe update some additional metadata or build a hash table. So it's not like immediately after I access page 1, I access page 2 and so forth. I have maybe a couple microseconds to go fetch the next thing and bring those in. So sequential prefetching, that's not that fancy. Actually, OS can do that in mmap. Like they can prefetch in sequential order both in forward direction and reverse direction. But what they can't do is index prefetching. Because again, it doesn't know what these pages represent. It doesn't know how they're connected to each other. It just sees a bunch of pages on disk. It doesn't know that there's a higher level logical data structure built on top of them. So in a database system, you can do things like, if my query wants to do a sequential scan, right? So I start at page 0 at the root. I jump down here to page 1. I bring that in memory. Now I jump here to page 3. But again, based on what the query wants to do, I know I'm going to have to scan along the leaf nodes to get more pages. But now the leaf nodes aren't contiguous, right? It's page 3, page 5, then page 6. So if you were doing blindly sequentially prefetching whatever is in order, you would actually go get page 2. But we don't actually need page 2 at all. We need page 5. So in some systems, like in Oracle, they can identify what pages I'm going to need based along the sibling pointers of the leaf nodes, and they'll go ahead and prefetch things for you. Right? And the OS can't do that. Yes?
Is it true that neighboring index pages are not necessarily close in memory?
Your question is it true that neighboring pages, so sibling pages along the leaf nodes of the data structure, they're not going to be contiguous in memory?
Yeah.
His question is like,
so for example, page 3 and 5, are they necessarily close in memory?
in memory? No. So there's no guarantee of the ordering in memory for the buffer pool manager. It might just happen to do it for prefetches things in an order, and they come out to be, I have enough frames to go fetch them in, and they're all contiguous, but not necessarily, right? Okay, now you're getting to like cache level or cache line optimizations, maybe what you're thinking about. disk is so much more expensive, we're trying to minimize that I/O, not worried about like keeping things in L3 cache. Okay. Another trick we can do is called scan sharing, sometimes called synchronized scans. And the idea here is that if I have 2 or more queries running at the same time, and they're accessing the same pages, then rather than them independently going fetching pages one by one, and maybe polluting my buffer pool, I can actually piggyback the queries off of each other. So as one query is scanning along, the next query shows up and jumps on the same cursor that's iterating through the pages, and just reads the same pages that the other query is reading. Right? So this is not the same as result caching. Result caching is query shows up, I produce some result, and then the same query shows up again, and then rather than running the query, I just reuse the cache result. This is like at the lower level of the actual implementation of the database system, I'm reusing pages that I'm accessing from multiple queries. So you can do this in SQL Server, DB2, Teradata, and Postgres. This is actually one of the nice features that Postgres has over other open source systems. Oracle sort of supports this, but the restriction is that they can only do this if the queries are exactly the same, like literally the same string is being passed in. Then they can recognize if these things are being running the same, running together at the same time. They're the exact same thing. I can reuse the results. So if you look at their documentation, they talk about how if you have a query select star from employees with lowercase and then with uppercase letter or an extra space here, these are considered different queries because the string's going to hash differently, so you can't reuse them. Whereas in other systems, these are logically the same query, and you can reuse the scans. So quickly, here's what this looks like. So our query starts, selects computing aggregation on table A. Query 1's ripping through, brings in pages as it needs as it goes along. Then now we get here to page 3, and we're going to go ahead and evict page 0 because it was the least recently used, and then bring in page 3. But now the next query shows up and wants to do basically the exact same thing. Right? Whether or not it has the same where clause, it doesn't matter. And if we did the stupid thing and started from the beginning of the page and scanned through like the first query did, well, what's going to happen? Well, we're going to have to bring page 0 back in, even though we just evicted it. So the data system can be smart and say, OK, well, you're accessing the same pages as this other query that's actively running. So let me just piggyback you, go along for the ride with the first query. It goes through, reads the same pages as and processes them in the same way that the first query does, which we can do, again, on the relational model because the data is unordered. Right? So we can exploit that here. And then now when Q1 finishes, with Q2, we kept track of, OK, well, I started scanning halfway through the table. There's a bunch of other pages I'm missing. So let me just loop back around and get the ones that I missed. Or maybe I'm lucky and there's a where clause that says I don't actually need to read other pages. Right? Now, what's tricky about this, which we don't need to show, is like depending what my query is, I may actually get a slightly different results if I'm filtering things out or have a limit clause, and I'm not sorting them in any kind of order because I can run Q2 once and maybe read these 3 pages and get some result, and then I run it the second time and I read the first 3 pages and I actually get back a different result. Again, on the relational model, that's OK. Right? If you had like a limit 100 here. All right, last optimization is a technique called buffer pool bypass. These are sometimes called light scans or originally invented in Informatics called light scans. And it's sort of similar to the buffer pool thing, the circular buffer I mentioned for Postgres, where I'm trying to avoid polluting the eviction policy tracking from other pages by localizing my access to a small subset of pages. But the idea here is that instead of always bringing something into the buffer pool and updating all that metadata, what if I just have a little memory buffer on the side just for my query? And when I go read a page in, I put it in that little buffer that only I can see. And then if I don't need it anymore, then I can just throw it away. And I don't have to go update the page table or anything else in the buffer pool manager. Right? So you would do this for like, you have a bunch of temp data. Like I create a temp table, write something out to disk, and then I got to bring it back in. And maybe I'll bring it back in and put it into to my private buffer because no one else can see it, instead of me putting it into disk back memory that's managed by the buffer manager. Again, this one is not as common, but this is one of the examples of what the enterprise systems can do that the open source ones cannot. All right, so just to finish it quickly, as I'll say multiple times throughout the semester, the data system is always going to be better than the operating system. And memory management is certainly one of those things where we don't want to allow the operating system to do anything for us because it's always going to be, just always going to make, not always the wrong decision, but it's going to make our lives so much harder. And because we know what's going to be inside the query plan, we can make better decisions on evictions, allocations, and prefetching and other optimizations. All right, so Wednesday next class will be, we'll kick off hash tables. Let me quickly talk about project 1. All right, so project 1 is going to be implementing your own buffer pool manager. After all the great things I said about it, you do the same thing. So there's to be 3 tasks. Implement your own replacement policy based on LUK, a disk scatter, and the actual buffer pool manager instance for them. And so we have basic APIs for all these components. You're essentially filling in and connecting all the pieces together. So the LUK policy, there'll be a class. You basically need to manage all that yourselves. It's up to you to decide what data structure you want to use to keep track of these things. It's OK to use things from the SDL. The disk scheduler will be responsible for doing a background reader-writer for requests. And this will be all based on using the SDL standard template library promises for callbacks. And it's very important that you use the latches to make sure this thing is actually thread safe, because we're going to hit it with multiple threads at the same time. Right? Basically, requests come in the disk scheduler, and you're responsible for writing things out to disk. And the buffer manager is going to sit on top of this, and it's going to have a page table to keep track of frames and run the eviction policy to decide when things get written out in and out to disk. Right? And it's super important to make sure you get the correct order for pinning, because that you may end up giving up something that you shouldn't have given up, and that gets overwritten, and that'll crash your program. Okay? So some general notes. I think 6 minute running, but there's a subset of files that we're providing you where you make all your changes. If you change any other file to do something weird, those are overwritten when you try to run it on GradeScope. We provide solutions only for the one task that we posted last night, because that was a late entry. But everything else is going to be sort of private. But we try to be very exhaustive in our testing. So if you get 100% on this, you should be good to go for the rest of the semester and not have any bugs. If you have any questions, please post in Piazza or come to office hours. But please don't ask us like benign or simple C++ questions. You gotta make sure, just like in Project Zero, you gotta make sure you write good code. So make sure you use all the formatting tools that we provide you. And then there is a leaderboard where if you get the highest, if your program is the fastest, it's a different test, it's a different benchmark than the tests, you get more bonus points for this project. Okay? And then whoever has the most bonus points at the end of the semester, you'll get some kind of bus tough swag. I think we still have sweatshirts, we have stickers, or other things to give out. Okay? All right, don't plagiarize, or you'll be ruined. All right, guys, see you tomorrow, and then see you on Wednesday.
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create rotate at a rate too quick to duplicate. Feel a breeze as I skate. Mics at Fahrenheit when I hold it real tight. When I'm in flight, then we ignite. Blood starts to boil. I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with third-degree burn from one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with same odds.